it's getting saved. So Mike, today what we are going to do is we are going to see TensorFlow, what is TensorFlow and how we can use it for different machine learning uh, implementations. So we have been studying about, or you already know about machine learning in the sense of linear classifiers or neural networks. So you're already familiar with those concepts. And in case you are not, then you are welcome to look at the course content of MLSP course EE603, which was taught in the last semester. And today what we are going to do is we are going to see how we use TensorFlow for implementing those machine learning concepts. Now, you already have a library called NumPy, right? And NumPy is very efficient to do mathematical operations like matrix multiplication, etc., right? Then why do we need something like TensorFlow? Yes. When NumPy itself is sufficient to do mathematical operations. Okay, one suggestion is that to write less code. Um, okay, but you can make classes and functions in NumPy. Why do you need TensorFlow for that? NumPy is not that fast with a large amount of data. That is another answer given by some of you. So, okay, this may be true. Yes, when you have lots of data, NumPy is not very efficient. Okay, this is one point well taken. Next is backpropagation gets very difficult. And to calculate gradients, yeah. So these 2 points are also very well taken, that uh, NumPy cannot perform differentiation automatically. Yeah, TensorFlow has autograde, which it can automatically do differentiation of a function with respect to the parameters. Yeah, GPU, yes. So TensorFlow integrates with the GPU very well, and it um, makes your calculations faster, basically. So these 2 points you have finally come to that. One is that for large data, NumPy is not very efficient, whereas TensorFlow uses GPUs, so it becomes more efficient in big data manipulation or big data processing. But and the second point is that TensorFlow has automatic gradients, which can differentiate a function with respect to the parameters, and that can be used for backpropagation or um, gradient-based update schemes, optimization schemes. Yeah, and other answer on the chat window is visualizing models and tuning them is easier using TensorBoard. Yeah, yes, I agree. TensorBoard has got many good functions which you can use to visualize your data and to or visualize your model and tune the model. That is true. But one can write such libraries even with NumPy. So that is not the pressing reason to use TensorFlow. That's not the main reason. Okay, so let's see how do we use TensorFlow, and especially the strength of TensorFlow, which is automatic differentiation. I will share my NumPy notebook with you, and let me share my screen. Okay, I will write step by step so that you can understand the whole thing. I will not share the entire notebook with you in one go, but I'll be working along with you, or it's kind of a live tutorial. Let me share my screen. First of all, I would like to write the references which you can refer to. There is a TensorFlow documentation available, and you can TensorFlow documentation is available on their website, and it has got very good tutorials, and especially there is a documentation of gradient tape, which explains how do we do automatic differentiation. And then there is one GitHub repo which I used. It's a simple IPNB code, which I use to take some of the code fragments which I'm presenting today. So the first thing you will do is you will import TensorFlow, right? And I would also like to import NumPy, because NumPy I'll be using for preparing my data essentially. Okay, so I have imported TensorFlow. Now, one important thing I should notice is TensorFlow version should be 2 or higher than 2, because TensorFlow 1 was a very different kind of syntax and very different kind of architecture. But TensorFlow 2 is the one which I'm using here and which I recommend you to use. This is Python 3 and TensorFlow 2. Okay, now let's see what is automatic differentiation. So what do you mean by automatic differentiation? You will have a function, let's say y is a function of x, and you will say y is equal to, let's say, x to the power, let's say you have y equal to x power 5. Right? Now, what will be your y for different values of x? I will say, let's say my x has some value, x is equal to 2. Then I will define a function. I will say y is equal to x power 5. And then I will say print y. It will give me the value of y, which is 2 to the power 5, which is 32. This is very much possible with NumPy. But if I ask what is the derivative of y with respect to x, that is something which NumPy cannot answer. So for that, I will be using TensorFlow. So how do we do? Same thing, just like we define the variables, I'll define the variable in TensorFlow. I will say, just, so instead of writing x equal to 2, I will x is assigned 2, I will say x is a TensorFlow variable now. I will be using a TensorFlow variable 2, and I will say this is trainable. What is the meaning of trainable? Trainable means basically it is a TensorFlow variable which is differentiable, or which, no, what do I say? It's a variable which you can change the value. And yeah, so this is how I define my x. Now I have to define y. Now to define y, I have to use something called gradient tape. So what is gradient tape? Gradient tape, so if I open gradient tape like this, and within this, whatever operations I perform, they are kind of tracked by the tape, and I can use the function then dy by dx is tape.gradient. So if I can use this function to compute the derivative, right? So I use gradient tape, and when I start the gradient tape and then I say dot gradient, this will actually compute. So this thing will construct a graph which saves the relationship between x and y, right? And then when I use this function tape.gradient, it will actually compute the gradient or the derivative and then return the value here. And then I can print y, and I can also print dy by dx. Now dy by dx is a TensorFlow variable. I can either print it like this. Okay, let me print it and then you will see. So yeah, see, my y now is a TensorFlow variable, and its value is 32, right? 2 to the power 5 is 32, as the same as the NumPy thing. And but my dy by dx now, it computes the gradient x to the power 5. So 5 into x to the power 4. X to the power 4 will be how much? 16. to the power 4 is 16 into 5. So it's 80. 16 into 5. So this is what we get. So it is computing the gradient perfectly, right? This is a very simple thing. This is how we do the gradients. That's it. Anybody has any questions here?
So why did we write that y is equal to x raised per 5 under that statement with tf dot gradient tape as tape?
Okay, so whatever you will write here, it will be dragged. Let's say I write here some z is equal to x to the power, or c equal to x to the power 2 x square. And then I can compute here dz upon dx also. Basically, this tape will keep a track of all the variables or whatever relations you define inside this. They will be tracked or watched by tape.
Okay, so it means if we want to take their gradient, they should be under that statement with tf dot gradient tape.
Yeah,
We can,
after you this tape will kind of note down all these relationships, and once
okay,
you're outside this, then you can use the dot gradient function of tape to find the gradient value.
okay, sir.
And let's say if I write dz upon dx equal to tape dot gradient z comma x. Now what will happen? What will happen? What will be the result? Z will be equal to what? 4,
That will be 4,
and dz upon dx will be
also 4.
also 4. Okay, so this will be same. Let's see what happens. Oh, it gave an error. Why did it give an error? It gave an error because you can use tape only once. When I use the tape for dy by dx, immediately the tape is destroyed, and then you cannot reuse it. So to be able to reuse it, you have to set a thing here called persistent equal to true. Persistent is set as true. Then this tape will not be destroyed. This tape will not be destroyed even when you use it once. Basically, you can use it multiple times. It will still persist. So now it should run. Yeah, see, now it is running. So it is 4 and 4. Okay, now if you don't want to see this uh, this whole thing, you can simply say y dot numpy. Then it will show you just the value, not the whole tf dot tensor, etc., etc. If I just say numpy. Will just show the value, not the whole thing, right? So basically, it construct it when I say dot numpy, then this is the graph object, or the TensorFlow variable object is you extract the value from there. Yeah. Any questions on this?
No, sir.
Okay. Now, what if you have multiple variables, not only single x, but let's say you have x1 and x2. Let me write it here. Let's say you have x1 is x1 is this, and you have another variable called x2, and then let's not use z can be there, but I'm just to save space, and so I can say now y is x1 to the power 5 plus x2 to the power something, what, 2 plus 5. This is my y. Now I have to compute the gradient with respect to x1. I can also compute the gradient with respect to x2. So what will be the values? With respect to x1, the derivative will be 5 times x1 power 4, which means 80. With respect to x2, the derivative will be 2 times 2, which means 4. And the y will be this whole thing. It's computed. That's it. So the same thing we got, right? So in this way, you can compute all the gradients. You can play around with it to see, okay, how you can, what all things can you do? For example, can you put together x1 and x2 and compute the gradient with respect to both? I did not try it, but let's do it. Let's see what happens here. Okay, I cannot use this dot numpy because I think it is saving as a list. Okay, yeah, there are two elements. One is 80, other is 4. Yeah, so yeah, it works basically. If you give as a list, then it will perform the gradient with respect to each element of the list and then return the list. Okay, anybody has any questions at this point?
Sir, will it just show a single value, or we can like have a plot or something? The derivative.
Plot means?
Like suppose when we define y is equal to x raised power 5, we can plot that. Then its gradient also can be plotted for x raised power 5x raised power 4, something like.
Okay, you mean to say that you are, yeah,
We if we don't define the x, then
you can define a function, right? Like for example, you can say define something derivative, and you can say some x, and then you can initialize like this, and then you can return dy by dx. Here, okay, your x will be a vector, so all this thing will not be required. Maybe you have to convert this. If this x is a numpy x, then you might have to convert it into a TensorFlow thing, right?
okay, yes,
Because you want to convert your numpy into TensorFlow variable, right?
yes, x will be basically a vector. Yes.
Yeah, yeah, and then it will return a vector in which you can plot.
Yes.
Okay, well, we can complete this code anyways. Okay.
Yes, sir.
Let's okay. Let me ask if anybody has any questions. Okay. Okay, fine, no problem. Then we go to the next concept which I want to discuss. What about higher order derivatives? What about double derivative or triple derivative? So that's also very similar. You define x is tf dot variable in this way, and y is this. I'm not doing z for the moment at the moment. Okay. Let's say I want to compute d2y by dx2. How will I do that? So same thing. I'll be defining two tapes now. The first tape for first derivative, the second tape for second derivative, right? I can, let's say, tape 1 and then tape 2 inside. Actually, this is 1, this is 2, because this will do the first derivative and this will do the second derivative, right? And then dy by dx is what? Tape 1 dot gradient, and d2y by dx2 is tape 2 dot gradient. Oh, sorry. Oh, sorry. This will be inside, right? Because this tape should be able to see whatever operations are happening, right? So when this tape sees that this is how you have computed dy by dx, now you will be saying my dy by dx is differentiated with respect to x, right? I want to differentiate this thing now. So I have to put this thing also inside this tape. Now this tape 2 knows how was y defined and how was dy by dx defined. So that now tape 2 contains the entire information. Now you are saying this is how I will be computing my d2y by dx2. Is this clear? Now tell me what will be the answer. What will it print? What will it print? Y is to the power 5, which is 32. dy by dx is 80, which was last time. Now, what is d2y by dx2? It is 5 times 4 times x cube. So x cube is 8, and 5 into 4 is 20. 20 into 8, 160, right? Let's see if it calculates. Yes. See, 32, 80, and 160. Double derivative is also working. In this way, you can compute as many derivatives as you want. Is that clear? Does that make sense?
Yes, sir.
Okay. So that's it. This is the concept of gradients in TensorFlow. Now, some things which you have to take care of is, okay, let's define persistent equal to true only when you want to use it multiple times. For example, in this case, you don't want to use it multiple times. So why to hold up your memory or computational resources, right? You will just not use it. You will say false. This will release as soon as once it is called, once your gradient is called, it will release all the resources. It will delete all the intermediate variables. So that's why you can say it is equal to false. Then your execution will be faster. Okay. Now let's do a real example. I will switch to my writing board for some time to discuss the example, and then I will come back to the coding part. Okay, so now what I'm trying to do here is I'm trying to do a linear regression model using TensorFlow. All of you have seen linear regression in MLSP course, and you saw there we defined a function. Let's say y is equal to um, y is some function of x, right? X was a there is some problem with oops. So Okay, I have my x equal to something, some number. It's a free variable, and my y is now a function of x. Y is a function of x, and I will say this is some a times x square plus b times x plus c. Now, what does this mean? I am defining a, a model which has how many learnable variables? How many learnable parameters are there? What are the learnable parameters here?
A, B, C.
A, B, and C. These three are my learnable parameters, and it's a parametric form. It has got a fixed form, and I want to just find the value of my variables. Now, what I will do is, okay, so let's assume there is an actual function, let's say y actual or y true, which is simply, let's say 6x squared plus 8x plus 2. Now note that this need not be in the same form as this, but we have kept it in the same form because we want to check the value which is estimated by our program is same as these values, right? So for our ease of evaluation, I have taken it in this form, but it can be of any other form also, right? Our model is of this form, our true underlying function can be anything. Okay, so, but for verification, I am taking it like this. Now, how do we learn these parameters from the data? So what we will do, first step is generate the data. So take some values of x is equal to some values, right? And correspondingly, you compute y true are the same corresponding value. Let's say that you have here 10 values. Here also you will get 10 values, right? Now what will you do next? You will define your model, right? Your model is y equal to define the model. So here your A, B, and C are the TF dot variables, right? Means I'm not writing in the perfect in the proper syntax, but just a pseudocode. Okay, and then third is what you train the model. And when you train the model, you will say, then you will be using that gradient tape, right? And inside the gradient tape, you will be defining all these functions that your y is this. That's it. And then there is a loss function you have to define, right? What is your loss function? What is the loss function? Yes.
L2 nor
Yes, very good. L2 norm or L1 norm, anything I can define. So I will basically say under my TF dot gradient tape, so under my gradient tape, I will first say my y is ax squared plus bx plus c. And then I will say my loss is equal to y minus y true. And then either L1 norm or L2 norm, right? Any one of them. And then I will say my gradients. After this is over, then I will here say gradients. Now, uh, basically dl by dA is equal to what? dl upon dA is tape dot gradient and here loss with respect to A, right? And then I will be updating my gradients, or updating my loss, updating my variable. A is now A minus some eta times dl by dA. Right? This is my gradient descent algorithm. And similarly, I'll do for B and C also, right? And then I will repeat this whole thing for n number of epochs, right? For, let's say, some 100 or 1,000 epochs. Does it make sense? That's how I do, right? And then finally, how will I evaluate the model? So evaluation. Yes, how do I evaluate the model? How do I evaluate the model? I will take some test data, right? Take some test data. Test data means here x comma y true, some different x, right, and y true, and then you find out or predict y as a function of x dash, basically y dash as a function of x dash, and then compare y dash and y true, y dash true. Right? You will be comparing them using some metric, or basically, okay, yeah, using some metric. Here, the metric could be either L1 norm or something, right? Mean squared error, etc. Or another way could be for evaluation, the way, because we have defined our, this is one way. But the other way which we can try here is, because we already know the true values of ABC because our original data was also in the same form. So we just check if my A is equal to 6, B is equal to 8, and C is equal to 2. Right? A should be equal to, what was it, 6, 8, and 2. 6. B should be approximately equal to 8, and C should be approximately equal to 2. I mean, this is a simple way which is possible in this case only. Right? Okay, is that clear? Is the theory clear? Yes? No?
Yes.
Okay. By the way, if you remember the previous MLSP course, there is a more efficient way to find the values of ABC. What is that? Instead of gradient descent, you can use something else also. Compute the values of ABC.
Inverting the matrix.
Yeah, yes. What was the name of it? Least squares estimate, right? Least squares estimate, right? So yeah, but yeah. So that is very simple. That is analytical. So basically, you can implement it analytically even in NumPy. You don't need TensorFlow for that. But in TensorFlow, what you can do is you can implement the gradient descent algorithm. So let's go to the code now and write the whole thing in the program. Let's write down. So first I will define my training set. So my X train is simply, you can take it as any array. It can be some random values also, no problem, but just that it's here. It is defined as 0, 1, 2, 3, 4, 5. Okay, and Y train is here 6x square plus 8x plus 2, which is the form which we defined. Okay, so these are all NumPy variables, right? As of now, TensorFlow is not introduced. So this was the step one. In step one, you generate the training data. In the step two, you define the model, right? So how do you define the model? We'll say my variables are, my trainable variables are A, B, and C, right? These are all TensorFlow variables now because you want to differentiate with respect to them. And now you have to do the training. For training, let's define the loss function first. My loss function is, so it is defined as the L1 norm, L1 loss function. Simply tf dot, okay, now notice that here, I did not use NumPy functions. I could, in general, we use np dot absolute real y minus prediction y, right? That was in NumPy. But now here, we want to differentiate the loss function. So I don't want NumPy variables. I want TensorFlow variables, which are differentiable eventually, right? So that their relationships are preserved. You don't want to compute the values, but you want to save the relationship so that you can differentiate. If I just save the values as is done in NumPy, then I don't know how these values were computed. But what TensorFlow does is it saves the relationship in the graph. The graph will say my real y minus real prediction, and the absolute value of this is the thing. So it does not save the values, but the whole relationship. Okay, now we can do the gradient thing. So how I will do that? First of all, I have to define the gradient tape, right? Inside the tape, okay, I will set persistent equal to 2 because I want to call it many times. No, okay. But anyways, we will see how many times we need to call it. And then you save all the relationships. The first relationship is my y hat or y prediction is a times x square plus b times x plus c. This is my model. And then my loss function, which is simply I am using this function, loss real y minus predict y, right? Now I need to compute the gradients. So how will I compute the gradients? I can either use, so I'll say a underscore gradients, b underscore gradients, c underscore gradients, and tape dot gradient, to use tape dot gradient, this polynomial loss, and then ABC, all the variables. Here I have defined them as a tuple. I can define them as a list also, no problem. Either list or tuple. Okay, now what next? Now I have to update the values of A, B, and C. I can say A is A minus A underscore gradients into some eta. Let us define eta somewhere. Eta is 0. This is not a TensorFlow variable. It can be a simple float number. Then similarly for B and C also. Okay, and what else? That's it. Okay, so here x is x train and y is y train. I can say real underscore x is equal to will it train? I don't know. but let's see. So it works. Let's compute the value. Let's see what is the value of A. A is 1.023, whereas, okay, let's compute all of them. A, they're very far from their actual numbers. Anybody can tell what is the reason?
Only one epoch has been done.
Yes, very good. So we have to perform multiple epochs. Now, how do I perform multiple epochs? So what I will do is I will put everything in a function, and then I will call that function with different or multiple times. And that function will be one epoch. Uh, we will call that a step function, means that is one step of training. And in this case, it is one epoch, but it could be also one batch. So in general, we call it as a step. And we don't use this. We pass real x and real y as inputs. And we compute these things inside. Okay. And then I have to call this step function multiple times. So I will define a loop in which I will say, means this is a dummy variable. Whenever you don't want to save that variable anywhere, just call it underscore. So this is being called 10,000 times. 10,000 times step x train and y train, right? That this x train and y train are passed to this function. Now this is a NumPy variable. These are NumPy variables, right? But it's all right because you don't want to perform differentiation with respect to these, so they are fine. You just A and B have to be TensorFlow variables. A, B, C have to be TensorFlow variables. Okay, let's see. Let's run this. It will give an error, but let's see why it will give an error. So it's giving an error because it does not like A. See, we didn't do anything to A except at this step. At this step, we said A is A minus A underscore gradients times eta. Now it turns out that this kind of a form is not acceptable to TensorFlow. So once you define like this, then you cannot really use this A again as a TensorFlow variable. So TensorFlow provides you with a another function which is called assign. So how you will say A dot assign. What do you want to assign it to? You can say A minus A underscore gradients into eta. Or another way you can do it is assign underscore sub. This is another function which basically a shortcut. So I will say B is equal to B is B minus B underscore gradient. So assign underscore sub. And another way is assign dot add, assign underscore add. This function will basically add. So you have to say minus C underscore gradients into eta. So any of these forms will work. But this kind of assignment will not work. Right? Equal to sign will not work, but this will work. Let's run it now. There's no attribute sign. That is bad. Okay, maybe we have to run it again because A is destroyed. Let's run it again. Now I've redefined A. Okay, it's running now. See, you can see the blue, the green arrow. It's moving. It's moving multiple times. Okay, it means it is doing something. Let's see how it returns the final outcome. Yes, it is done. This step is over. Let's now print the values of ABC. Yeah, you can see 6, 8, and 2. These were the ground truth values, right? 6, 8, and 2. And we are getting 5.96, which is almost 6, and 7.58, which is almost 8, and 1.999, which is almost 2. So we are getting 6, 8, and 2 here, right? Okay. Is that clear? Is that clear?
Yes, sir.
Yeah. So we used our gradient tape to compute the gradients and then to compute the values or update the values of A, B, and C, our variables in the loop, right? And we noticed that we should not use the equal to kind of assignment so that the TensorFlow is the TensorFlow graph is still preserved. Okay. Now this was the linear classifier. Now let's see how do we train a neural network using gradient tape. Should we do that, or should we, do you have any questions before we proceed to that? Are there any questions? Yes, no?
No, sir.
Okay. So now I will dive into MNIST data, which is a very standard data set. You can use Iris also. I've just used this because just for illustration, nothing. You can use it for, basically to show you how any neural network you can train. So this is how we are doing it. We are importing different layers of dense network. For example, convolutional layers, flatten, dense layer, dropouts, max pooling layer. And we are using here the sequential API and not the functional API, but you can also use the functional API to define your neural network. And then we are using an initializer, and an initializer is basically to initialize your network parameters. It's just a random normal initializer. And then we are using data sets. From data sets, we are importing the MNIST data set. And then we are using Adam optimizer. Yeah, so I think these are, let's run it. First of all, we will prepare the data, and I'm sure you are familiar with MNIST data by now. MNIST is a very standard data set. It basically consists of images. Your X are the images. These are what do you say, black and white images, and Y are the labels corresponding to it. For example, you can say my Y is either 1, 2, 3, 4, etc. So let's print some values. I will say print 0. Oh, not Y, sorry, it's Y train. So this is a one hot vector, right? When I use this function, to categorical, it is converted into a one hot vector. So it means 0, 1, 2, 3, 4, 5. This number is 5. So the X0 corresponds to the image of, or handwritten image of the digit 5. Let's see, X train. What is X train? It won't show it properly here. We have to plot it, and then yeah, it doesn't show it properly here. Oh, can see it's okay, very bad. Yeah, but basically it is an image, so we'll have to plot it. Anyways, I will not do that. I'm sure you're all familiar with MNIST data. Now, next, what do we do? First step is we prepare our training and test data. Second step is we define our model. Let's define our model. And this is a very standard way of defining the model. You just put the conv layers together. And there are some hyperparameters: batch size, epoch, number of epochs, optimizer. We are using Adam optimizer with a learning rate of this much. Initial learning rate is this much. And then weight initializer is our random normal. And the model is simply a sequential model which has conv layer of 32 kernels, where each kernel is 3x3, followed by ReLU activation. And then next layer, again a conv layer of 64 kernels, 3x3 and ReLU activation. And then we have a max pooling 2D. We're doing some pooling to reduce the size of each output. And then we are using a dropout. This is a kind of regularizer, so what is the use of dropout? What is the use of the dropout?
Yes. Regularization.
What is regularization?
To make sure the model generalizes well.
Yes. And how does it happen geometrically? How can you explain this?
It prevents any weight vector, any weight from shooting too high.
Yeah. It prevents any no, it prevents local minima, right?
It prevents overfitting.
Yeah, it prevents overfitting. It prevents the value of weights getting stuck in some local minima. Yeah, all these things are called regularization, and dropout does that. And then you have a flatten layer, which basically your output is a three-dimensional block. It will just flatten it into a single vector. Everything is just reshaped in a single vector. And then you have a dense layer, which will basically map this flattened vector into 128 classes. And then followed by a dropout layer, you have another dense layer, which finally maps everything to 10 classes. This is your final layer. And here, that's why you're using a softmax activation, because you want to do multi-class classification. And yeah, that's how you define your model. We run it. And then if you want to see how your model looks like, you will be using model.summary command, which will basically show you conv2d layer, then conv2d layer, then max. Everything is put together here. And also the number of parameters is also put together. It's 1 million parameters. It's a large model, but anyways, that's how it is. Now you have to come to the training part. Now model is defined, data is defined. Now you have to train the model. How will you train the model? So let's see how we defined it earlier. You defined a step function, which takes as input your numpy x and numpy y, right? And then you have a gradient tape, which has got, how do you find out your model prediction y in terms of your model and x, basically model parameters and x. And then you have some loss function, which will compute the loss. And then you have the gradients, and then you update your parameters. So we'll follow exactly the same steps. So same thing, step function, which basically is one step of training. In this case, it will be one batch, because MNIST data is large. We don't want to do everything in single go. We will do them in batch batch-wise fashion. So we have gradient tape. This tape will measure your gradients, and the model is prediction-wise. Now you apply this model on your X, and there is some reshaping requirement by Keras because we are using Keras here, right? TensorFlow.Keras. So it requires your model to be in certain format. So we are doing some reshaping here. And then we are computing the loss. The loss is categorical cross entropy. Now, Keras has already defined this loss function for you, but you need not use that loss function. You can also define your own loss function. And it could be anything, maybe a categorical cross entropy plus something else plus something else. You can define your own loss function, just like we did it in case of our linear regression, right? And then you can just evoke that function here or call that function here, and that's it. So, but the tape is watching all these relationships, and it is keeping track of them. Then finally, you come out of this tape thing. You will say, let's compute the gradients now. Now you have to tell what are the variables with respect to which you are computing these gradients. So you will be using model.trainable variables. This is the list of all the trainable variables inside the model, the weights and biases, etc. And then model loss is the function which you want. This is your y and this is your x. dy by dx is here. Now you have to apply these gradients to the parameters. So you can use a dot assign underscore sub or something, but Keras does it for you. It has made a function which does everything for you. Basically, this function does the same thing: apply underscore sub, and then the weights. Sorry, the gradients here. So that's how you are applying the gradients. Okay. And then what is next? Let's run it. This is just defining a function. Now comes the next part. You have to now run all the data through this function. So I will do it batch by batch, and how it happens. So first of all, we compute number of epochs, right? So in one epoch, you have got, we have defined a batch size here, right? We defined that we want to use only 128 samples in per batch. So the whole data divided by 128 is the number of epochs, or sorry, the number of iterations I need to run, and or number of batches basically. And then you have in each epoch, you will do this thing, right? N is my some running variable, and steps you are passing your data through this step function, and in a batch, basically you can do shuffling, etc. also, but here this code is not doing any shuffling. It just runs from 0 to batch size, and then batch size plus 1, or batch size to 2 times batch size, etc. Right? You can do shuffling also here. That's it. And then you finally you run this step, but now this thing will take a long time to run. Do you know a way to speed it up? This will take a long time to run on this machine. This is Google Colab.
GPU?
Yes, you use GPU. So you go here and you say view resources or manage session. If you go to view resources, it will show you that you are using this much RAM and you are using this much of disk space. But if you go to manage session,
so go to runtime.
Oh, it does here also. Oh yeah, change runtime. See, in this only, in resources only, here change runtime type. Here you go to GPU. and then you say save. And now it is reconnecting. Now whatever we had computed, that is lost. I have to run it again now. So now you see you have got a RAM, which is almost empty, and you have got a GPU, and GPU has its own RAM, which is also empty at the moment, and some disk space. Now you have to run the whole thing again, and then you run this training function, and that will give you the trained network. And then you will be running your model through it. Basically, you will say, I'm not running it, just you can, but it's very fast. It's very fast. So you compute the accuracy. This is a shortcut method. I don't recommend it, but okay, this is how we are doing it. That you can first compile the model, which basically will run everything for you. And then you will say model dot evaluate, which will evaluate the model. Instead of doing evaluate dot model, you can say here, you can say y is model dot predict x test, right? So in this way, I will compute my estimated y, and then I can compare it with the original y, and I can compute any matrix which I want. For example, confusion matrix, or the F1 score, or accuracy, etc., etc. Precision recall, whatever you want, you can compute once you know the predicted y and the true y. And you can also print these values. Means you can make an Excel sheet or a CSV file which has something like this. You can say with open some file, let's say output.csv, comma, write as fid. So you can say print, you can first run a loop for I in range length of y, and then you will say print here. You can print you can print first. Let's say there is, every file has got some label. In this case, we didn't have any label for the file because we are not reading these x from some file. Rather, it's just given to you as a numpy array. But you can maybe here, if you are reading the data from some file, you will print some file name, right? And comma, you will print y underscore test, which is the true value I, and then you will print y I, and this will print everything in the, okay, and then you have to say, I forgot the format, maybe out equal to fid or something. I forgot the exact format. So this will print everything, and okay, and the new line is automatically inserted by the print command. Yeah, this just verify this syntax. I don't remember exactly. So then everything will be printed in a file, and then you can do error analysis, that which are the files, or here in this case, it could be just I, which are the files which are giving error. And then you can look at the data, then why is it giving error? Is there some obvious reason that it is giving error, or is there some means it is just model is not able to capture them perfectly, or the data has some outliers, etc. So this will be useful for your error analysis. Okay, is that clear? Is that clear? So we started from very basic understanding of what is gradient tape, how we define variables in TensorFlow, And then we went on to see double derivatives and multivariate um, functions. And then we saw a simple linear classifier, or linear regression model, and how do we train it? How do we update the weights in various epochs? Then we came to the neural networks, and we defined a standard kind of network, and we trained our model using the gradient tape. Okay. Anybody has any questions at this point? Yes. Okay, no questions. Fine, then we can stop here. And I would request you to use this knowledge now to make a normalizing flow model which maps an input. The U distribution could be either uniform distribution or normal distribution, any simple normal distribution. And then you are mapping it to a complicated distribution, maybe a mixture of Gaussians, a GMM distribution. And then let's say you have only the samples available. You don't have the PDF function available. You only have the samples from the target distribution. And then the next problem could be when you don't have the samples, but you have the function values, means the probability values available. That could be the next case. So we saw both these cases in our discussion on normalizing flows. So you can use all this information to program them. Can you do it? Yes. Okay, then we stop here. See you. Okay, Wednesday is a holiday because of Republic Day. See you on next Monday. You have 1 week time, so go through it, assimilate it properly, and then we'll meet on Monday.
So will you share this code also along with the
Yes,
lecture
I will
recording?
share. I will put this code in the shared folder. We have a shared folder, right?
Yes,
Yeah, I will put it there.
I think.
Okay, thank you.
Sir,
Yes.
sir, I had a question regarding coding of the normalizing flow. So when I was trying it, I was getting stuck on when I was trying to use neural network as a transformation function. So when I was trying to use the flipping technique, how would it affect the determinant of the Jacobian after flipping?
Your determinant is basically
Sigma 1,
F.
sigma 2
Yeah,
multiplications.
sigma 1 into sigma 2.
Yes, sir.
So that's it. So how does it affect? Okay, so when it is unflipped mode, then your sigma 1 is 1 always, right? And sigma 2, basically in the Jacobian matrix, the 1,1 entry or 0,0 entry is 1, and the other entry is sigma. And when you flip, then this will also flip. Then the first entry, 0,0 entry will become sigma, and the 1,1 entry will become 1. You don't have to implement it over and over again. You just flip the inputs themselves. Right? Instead of calling it as x1, x2, you now pass x2, x1 into your function. Then automatically it is flipped. Or inside the function, you can define a flag called flip equal to false. And then you say if flip, then x1 becomes x2 basically. Right?
Okay, that's basically alternatively flip it.
Yeah, you define a flag called flip as an
Okay.
input to your function. Okay. Thank you very much. See you on next Monday.